Hello everyone, today I will give a report for our paper whose title is Spoofing-Aware Attention-Based ASV Backend with Multiple Enrollment Utterances and a Sampling Strategy for the SASV Challenge 2022. This page shows the outline of my report. First, I will give an introduction to this task, and next I will give a review of our previously proposed attention backend. Next, I will give the details about our spoof-aware attention backend from three aspects. Next is the experimental results and analysis. Finally is the conclusions. First, let's say conventional automatic speaker verification system. An ASV system can distinguish whether the access speakers have been enrolled or not via their voice. The enrolled speaker is target, otherwise it is a non-target speaker. However, there is a risk existing in conventional ASV system. For example, in this figure, the yellow face is a real speaker and the pink face is a cloud speaker generated by TTS or voice conversion system to simulate the real speaker. In this occasion, the ASV system may fall down in authentication. Let's say this table. Encapsulated is a sort of ASV system. If we only consider the non-target attack, we can say this system works well from the SASV EER number. But if we also consider the spoof attack, the performance of encapsulated will decrease heavily, like this. Next, let's say the details about the spoof-aware speaker verification challenge. The purpose of this challenge is to bridge the gap between the study of ASV and countermeasure systems and corresponding research communities. Next is to extend the ASV scenarios to take spoofing attacks into account. The organizers of this challenge provide the pre-trained encapsulating for ASV and pre-trained assisted model for countermeasure. As for our proposal for this challenge, we first extended our attention backend to be spoof-aware via ensemble backend model. Next, we use a sampling strategy to simulate the new spoofing-aware verification scenarios introduced in the spoof-aware speaker verification challenge. Next, let's review our previous work called attention backend because our proposal for SASV challenge based on this work. First, let's say the model architecture. In this model, we first extract the enrollment speaker embedding by the pre-trained speaker encoder. And next, we stack the all enrollment speaker embedding as a matrix denoted as a capital E. Then we use scale self-attention to explore the interrelationships among all enrollment speaker embeddings. And next, we use another attention mechanism called the feedforward self-attention to aggregate a varied number of the enrollment speaker embedding by adaptive weights. Finally, is the logistic regression-based score calibration. In this way, we can map the score to probabilities. We can map the raw score to a probability score for fair comparison. In the attention backend, we also design a specific trial sampling method for training. Because in this way, we can introduce the multiple enrollment process in training stage. First, we load the speaker balance the mid-batch from a dataset. For example, in this table, there are 3 speakers A, B, C, and each speaker has 4 utterances whose index range from 1 to 4. Then we rearrange the mid-batch to form trial pairs, testing and enrollments. First, let's say the positive trials. The positive pair. First, the test trial and the enrollment data are from the same speaker, and one test trial is selected from the speaker's data, and the rest are left for enrollment. Next, let's say the negative pair. For the negative pair, the pairs marked by the check symbol for test trial and the cross symbol for enrollment of other speakers included in a mid batch. However, in this trial sampling method, it only considers 0 if for the imposters, which is also called non-target speakers only. Next, let's say the loss functions for attention backend. In this work, we use a weighted sum of binary cross entropy loss and end-to-end generalized end-to-end loss. We use the former to distinguish the positive and negative training samples, and use the latter to enlarge the gap between the negative and the positive boundaries. After reviewing the attention backend, next let's say the proposed spoofing-aware attention backend for SASV challenge. Let's say the model architecture of a spoof-aware attention backend. First, let's say the enrollment part. The enrollment part is same with the original attention backend. And next, we introduce the two branches for ASV and countermeasure respectively. As for the ASV branch, it's same with the attention backend. We can, after use the sigmoid function, we can get the probability score for ASV task. And as for the countermeasure task, we also designed the simple neural network with a linear transformation and a sigmoid function to map the embedding of the countermeasure as a probability score. These two branches are independent, but next we can concatenate these two scores as a vector and use another linear transformation to map this score to a probability score for final decision. In this way, we can introduce the joint training for the two independent branches. So the introduction between these two branches will be introduced by gradient backward propagation algorithm. Next, let's say the sampling strategy for SASV challenge. First, it's same with the attention backend. We load the M speakers and K utterances per speaker from the dataset. However, please note that one speaker in a mid batch has half bona fide and half spoofed audio files. For example, let's say this table, there are 3 speakers and ABC, and each speaker has 4 utterances. But for each speaker, they have 2 utterances spoofed audio and 2 utterances are real bona fide audio. Next, we also arrange the mid batch to form the trial pairs. First is the positive pair. The genuine test trial and the enrollment data from the same speaker. One test trial is selected from the speaker's data, and the rest are left for enrollment. As for the negative pair, the pairs marked by the pairs marked by the check symbol and the enrollment marked by the cross symbol of the other speakers, or spoofing test trial included in a mid batch. The advantage of this sampling strategy is that we can simulate the SASV scenarios. However, in the disadvantage of this sampling strategy is it will cause unbalanced positive and negative trials. To alleviate this unbalanced problem, we use hard binary cross entropy loss function. As for the loss function is a hard binary cross entropy loss. In this loss function, we select all positive samples only and use only the top n most difficult negative samples when computing the cross-entropy loss for backward propagation. In our experimental setting, we only use the n equals to 100. Next, let me show the experimental results. First is the dataset. In this challenge, it provides 3 datasets. The Voxlab2 for training ASV system and the ASV spoof for 2019 training partition for train countermeasure system, and also the development partition for the adjust the parameters of the hyperparameters of the model. And they also provided 2 pre-trained model called eCapitalian for ASV and assist model for countermeasure. Finally is the evaluation metrics. In this challenge, they use 3 different metrics. The first is the conventional speaker verification EER, and the next is the for the countermeasure. The next is the EER used for the countermeasure system. It called the SPF EER. It was used to evaluate the performance of the countermeasure systems. Finally is the SASV EER. In this situation, this metrics consider both non-target and spoofing tags as the impulse as the negative, and only the target speaker, real target speaker, as a positive samples. And this challenge gives 2 baseline systems. Backend fusion by using backend fusion method. The first is the score fusion, just some score for ASV and the countermeasure module for this agent, and the next is the in-binding fusion. In-binding is extracted from the pre-trained ASV and the countermeasure models are fused via the simple feedforward neural network with 3 layers MLP. Next, let's say the challenge result and analysis. This table is the result we got from our experiments. First, let's say the first line. It shows that the SOTA eCapitalian based ASV model is vulnerable when attacked by the spoof data, because we can find that the ER of the SASV EER is decreased heavily to the SASV EER. And next, let's say the second line. Just simply summing the ASV and the countermeasure scores can alleviate the vulnerability of the ASV model to some extent. However, it's still unacceptable. Next, let's say the first and the fifth line. Attention backend model supports the eCapitalian, but it's also vulnerable to spoofing attack. Then, after extending the attention backend by using our proposal method, it becomes robust to the spoofing attacks while preserving the original ASV performance. We also conducted a post-challenge analysis by an experiment. In this experiment, we want to explore the effect of the attention mechanism in the proposal model. So, in this experiment, the attention module is replaced by a simple averaging operation without any learnable parameters. This table shows the result of the experiment. From the table, we can know that SPF EER is improved, which indicates the influence of countermeasure on the final score seems to increase. And the ASV EER and SASV EER results degraded. It appears that the attention module for the enrollment utterances is also necessary to maintain good ASV performance and robustness against spoofing attacks. Finally, the conclusions. The conventional ASV system is vulnerable to spoofing attacks, and the ensemble backend model using speaker and countermeasure embeddings can be robust to spoofing attacks while preserving the original ASV performance. In this paper, the score fusion and the attention modules in the proposed spoofing-aware attention backend model are complementary to realize best performance. This page shows the reference for my presentation. If you are interested about it, please have a look. Thank you.